The Large Hadron Collider has been recording B-mesons decaying into electrons about 15% more often than they decay into muons, and the standard model says that should never happen. Why is the most powerful physics machine on Earth producing data it cannot explain? And what does it mean when the numbers stop agreeing with the theory that built the experiment? This is not about a new particle appearing as a clean spike in the data. This is about a ratio that refuses to match prediction, a signal that flickers instead of strengthening, and a question that forces physicists to ask whether their prepared categories are too narrow for what the machine is actually seeing. By the end, you will understand what the anomaly eliminates from the old model, what it still leaves unresolved, and why the classification itself has become the crisis. The first small payoff is this. When a fundamental symmetry breaks in a measurement, the issue is not whether something new exists, but whether the framework used to interpret the data was ever complete. One concrete reality check you can verify right now is that no experiment since 2012 has found a single clean new particle at CERN, making these messy decay anomalies the only active lead in high-energy physics. The default story is simple. The standard model treats electrons and muons as identical except for mass. This principle is called lepton universality. It says that when a B-meson decays, it should produce an electron or a muon at the same rate once you adjust for the mass difference. For decades, this rule held. Detectors measured decays. Ratios matched predictions. The model worked. Then the Large Hadron Collider beauty experiment, known as LHCb, began tracking rare B-meson decays with extreme precision. These particles contain a beauty quark, also called a bottom quark, and they decay in ways that are sensitive to forces beyond the ones we know. The LHCb detector was built to catch these rare events and measure their outcomes with enough accuracy to expose tiny deviations. What it found was not a spike. It was a ratio error. B-mesons were decaying into muons about 15% less often than the standard model predicted. The mismatch was consistent. It showed up across multiple decay channels. It persisted through different data runs, and it violated lepton universality. The contradiction is not that the data is noisy. The contradiction is that the data is clean enough to see a pattern, but the pattern does not fit the category. Lepton universality is not a preference. It is a symmetry. If it breaks, something is coupling to muons differently than it couples to electrons. The standard model has no mechanism for that. The old model predicts a specific branching ratio, the number of times a B-meson decays into an electron pair versus a muon pair. LHCb measured that ratio and found it lower than expected for muons. The gap is 15%. That is not a rounding error. That is a structural deviation. If lepton universality holds, the ratio should be 1. The measurement says it is closer to 0.85. The difference is small in absolute terms, but it is large compared to the precision of the theory. The standard model does not have a dial you can turn to make muons less favored. There is no known particle, no interaction term, no symmetry-breaking mechanism that predicts this outcome. The result forces a choice. Either the measurement is wrong or the model is incomplete. The statistical significance is the next anchor. In particle physics, a discovery requires 5 sigma, a 1 in 3.5 million chance that the result is a random fluctuation. This anomaly has been hovering near 3 sigma for years. 3 sigma means roughly 1 in 1,000. That is not enough to call it a discovery, but it is too high to ignore. The tension comes from the fact that more data has not pushed the signal cleanly past the threshold. Sometimes it strengthens, sometimes it weakens. It flickers. A clean new particle would grow more obvious with more collisions. This signal has stayed stubbornly ambiguous. That behavior suggests either a statistical mirage, a subtle instrumental bias, or a real effect that is being washed out by overlapping background processes the model does not fully account for. The flickering does not kill the anomaly. It changes the question. If the signal is real, why does it resist confirmation? One explanation is that the effect is not coming from a single heavy particle you can directly produce. It is coming from something that only shows up indirectly through quantum corrections. Virtual particles that never appear in the detector can still alter decay rates. A heavy, unknown particle, even if it is too massive to create at current energies, can leave a shadow in the data by shifting the probability of known processes. That shadow is what LHCb might be seeing. The standard model includes virtual particles, but only the ones we already know. If a new particle exists, even one far beyond the reach of the collider, it can change the math. The ratio error becomes a probe. The B-meson decay is sensitive because it is rare. Rare decays happen through processes that are already suppressed in the standard model. That makes them vulnerable to contamination by new physics. Even a tiny contribution from an unknown force can shift the rate by a measurable amount. The rarity is the feature, not the bug. It turns the decay into a precision test. The LHCb detector was designed to exploit that sensitivity. It tracks particles with millimeter resolution, reconstructs decay vertices, and separates signal from background, with algorithms trained on billions of events. The measurement is not easy, but it is not guesswork. The question is whether the correction for known backgrounds is complete. One possibility is a particle called a leptoquark. Leptoquarks are hypothetical particles that couple to both quarks and leptons. They do not exist in the standard model, but they appear in many extensions of it. If a leptoquark exists and couples more strongly to muons than to electrons, it would produce exactly the kind of ratio violation LHCb is seeing. The leptoquark does not have to be light. It can be heavy, beyond the direct production threshold, and still affect the decay through virtual exchange. The math works, the signature matches, but no one has seen a leptoquark directly. The idea remains a model, not a confirmed particle. Another explanation is a fifth force. The standard model has four fundamental forces: gravity, electromagnetism, the strong force, and the weak force. If a fifth force exists and interacts with muons differently than with electrons, it would break lepton universality. This force would have to be weak enough that we have not seen it in other experiments, but strong enough to shift B-meson decays by 15%. That is a narrow window, but it is not impossible. Some theories predict forces that only appear in specific conditions, like high energy or the presence of heavy quarks. The B-meson environment might be one of the few places where this force becomes visible. The idea is speculative, but it is bounded by the data. The Fermilab muon experiment adds weight. In the United States, a separate experiment measured how muons wobble in a magnetic field. The wobble, called the anomalous magnetic moment, depends on all the forces acting on the muon. The standard model predicts a specific wobble. Fermilab measured a different one. The mismatch is about 4 sigma. It is not quite 5, but it is close. And it involves muons behaving differently than expected. The two anomalies, one at CERN and one at Fermilab, might be unrelated, but they might also be two symptoms of the same hidden physics. If a new particle or force couples preferentially to muons, it would affect both the decay rate at LHCb and the magnetic moment at Fermilab. The coincidence is not proof, but it is suggestive. It turns two isolated hints into a potential pattern. Bell 2 in Japan is running a cross-check. The Bell detector studies the same B-meson decays using a different machine and different methods. If Bell 2 sees the same ratio violation, it rules out a CERN-specific error. If Bell 2 does not see it, the anomaly weakens. Early Bell data is compatible with both the standard model and the LHCb result, but the uncertainty is still too large to decide. More data is coming. The cross-check is not optional. It is the only way to know whether the signal is real or a machine artifact. The 4-lepton anomaly is another thread. Some LHC events produce 4 leptons, 2 electrons and 2 muons, or other combinations. When you plot the combined mass of these lepton groups, most events spread out as expected. But there is a small clustering around a specific mass value that does not match any known particle. The clustering is faint. It is not a sharp peak. It looks more like a bump in the background. CERN has labeled it structured background with undetermined origin. That phrase means the data does not fit the noise model, but it also does not fit a clean signal model. The source is unknown. The pattern is real enough to measure, but not clear enough to classify. It is another ratio problem, another case where the data refuses to sit inside the expected categories. The broader pressure is classification. Particle physics works by sorting events into known types: background, signal, or error. The standard model provides the sorting key. When an event does not fit, you check the detector, check the cuts, check the simulation. If the mismatch persists, you either expand the model or accept that the data is telling you something the model cannot encode. The B-meson anomaly is not a single event. It is a persistent deviation across multiple channels, multiple years, and multiple analysis methods. The signal is not strong enough to declare a discovery, but it is strong enough to demand an explanation. The standard model does not have one. Since the Higgs discovery in 2012, the LHC has not found another clean new particle. Every search for supersymmetry, extra dimensions, dark matter candidates, and heavy resonances has come back empty. The energy frontier has not opened. The precision frontier is what remains. The B-meson anomaly is the strongest active hint that something is wrong, but it is a hint, not a confirmation. The fear is that physics is entering a desert, a long gap in energy where no new particles exist until scales far beyond what any collider can reach. If that is true, the only way forward is precision. Measure known processes so carefully that even tiny deviations become visible. The LHCb result is exactly that kind of measurement. It does not require higher energy. It requires better statistics, better background control, and better theoretical predictions. The current LHC run, called Run 3, is designed to provide all three. Run 3 is collecting more data than any previous run. The goal is to either push the B-meson signal past 5 sigma or make it disappear. Both outcomes are useful. A discovery would confirm new physics. A disappearance would tell us the anomaly was a statistical fluctuation or an unmodeled background. Right now, the signal is stuck in between. It is too strong to ignore and too weak to trust. More data will force a verdict. The look elsewhere effect is a statistical trap. When you search through a large dataset for any kind of anomaly, you increase the chance of finding a random fluctuation that looks like a signal. The more places you look, the more likely you are to see something that is not real. Particle physics accounts for this by adjusting the significance threshold. A 3 sigma signal in one specific channel is more convincing than a 3 sigma signal found after scanning 100 channels. The B-meson anomaly was not found by blind searching. It was predicted by theory as a sensitive place to look. That makes the signal stronger, but it does not eliminate the possibility of a mirage. Only independent confirmation can do that. The core question is not whether CERN has found a new particle. The core question is whether the data can still be classified inside the standard model, or whether the model itself is too narrow. The evidence eliminates the simplest explanation, that lepton universality holds perfectly and the measurement is wrong. The data is too consistent, too well checked, and too persistent for that. What the evidence still leaves unexplained is the mechanism. If lepton universality is broken, what is breaking it? A leptoquark? A fifth force? A dark sector interaction? A quantum effect from a particle too heavy to see directly? The data does not yet have the resolution to choose. The measurement shows the violation. It does not yet show the cause. The strongest interpretation is this: the standard model cannot account for the B-meson decay ratio without adding something new. That something could be a particle, a force, or a correction term in the theory. But it is not optional. The numbers do not close without it. The anomaly is not proof of a specific theory. It is proof that the current theory is incomplete in this corner of the data. What remains unresolved is whether more data will sharpen the signal into a discovery or dilute it into background. Whether Bell 2 will confirm or contradict. Whether Fermilab's muon result and CERN's B-meson result are connected or coincidental. And whether the four-lepton clustering and other faint anomalies are early signs of the same hidden structure or unrelated noise. What this changes is the way physicists read the data. For a decade, the expectation was that new physics would announce itself with a loud signal, a bump in the mass spectrum, a sharp excess, a clean discovery. The B-meson anomaly is teaching a different lesson. New physics might arrive quietly, as a ratio that does not match, a symmetry that bends, and a category that no longer holds. The evidence is not dramatic, but it is undeniable. The standard model predicted one outcome. The detector recorded another. And no amount of recalculation has made the gap disappear. That is not a theory. That is a measurement. And the measurement is still waiting for an explanation. If you want to see how precision becomes the new frontier when energy runs out, this is what it looks like. One ratio, one persistent error, and one question that refuses to resolve.